As it was mentioned, I want to make a plea for cross-validation and scattered data approximation. So first of all, let me start off with the setting. So we are in a typical learning scenario. So we have some samples, namely n samples, which are distributed according to some rho. You can have tomographic data here, but what I have in my mind for the simplicity of the talk, we have xi coming from some interval and yi simply being some function values. And now one is interested in reconstruction. So having these samples, we would like to reconstruct our f back. And we have seen in the previous days and also today many algorithms which do this. And they may also involve possible parameters. And our question was, out of this big zoo of possible algorithms, how to choose the one which suits our application. So we would like to have something like an indicator of the goodness of fit. And what first comes to our mind is the risk functional. Here is the risk functional with respect to the squared loss. So this is basically the L2 error. But what you can see is that this involves the distribution itself. And if we would have this, this would make the problem obsolete. So instead, we have to work with what we are given, namely our data samples. And one method which does this is cross-validation. So briefly, what cross-validation does, it splits the set or the training samples in a training set and a validation set. And especially in leave one out cross-validation, you train the data on a set where one node is omitted. You evaluate that model in the node which you left out and compare it to the value which is given there. Now you do this for every one of these nodes. So one has two immediate drawbacks from that. First one being you have to set up n models. This could be computationally quite expensive, but as it turns out, in many scenarios, you can reduce this cost tremendously, basically to the cost of setting up the reconstruction itself. But the second question, which turned our interest, is for a theoretical foundation. So there is this Bakushinsky veto, which says that there exists a possible data realization such that if I have a purely data-driven method, such as this, basically we have no guarantee for the error. So instead, so far the statements are made in an asymptotic fashion or in an expected value. So if the nodes go to infinity, but we are seeking for pre-asymptotic results, and to circumvent this Bakushinsky veto, our results will hold with high probability, as it is very common in learning theory. And being in learning theory, we also use tools from there, namely concentration inequalities. So let me make a quick interlude on concentration inequalities. Here is Hoeffding's theorem. So we have n random variables originating from the unit interval. We let m be the expected value of the mean. And now the theorem tells that if I have my mean, all our realizations will be within an interval around this with high probability. So if I would like throw dice, then 90% of the times I will be in that interval. And I have this parameter epsilon with which I can tune how wide or narrow my interval is. And this, of course, is also then in the probability. But we would like not to have a sum here, but instead would also like to plug in the risk or the cross-validation score itself. But for that, we have to make some assumptions on a function which we would like to plug in here. And this will be done in form of C-boundedness. So we call a function to be C-bounded. So a function from n variables is C-bounded if and only if when I wiggle in one node, here it's the ith component, then this is bounded by some constant. So it's somewhat related to Lipschitz continuity, but I don't have the difference of the nodes on the right-hand side. And with that probability, I can now formulate a generalization of Hoeffding's concentration inequality. which is due to McDiarmid. Here we again have n random variables, now originating from arbitrary domain omega. We have now f, which we assume to be C-bounded on that domain. We have m, again, the expected value. And now we have the same as before, but instead of a sum, we have here this f. So again, we can bound all the data realizations around their expected value with high probability. And later we want to replace this f by the risk or the cross-validation score. And for them, we cannot show the C-boundedness for the whole domain, but rather for a subset. So we need another generalization of this concentration inequality. And this one is due to Richard Combs. We have again the random variables on our domain omega. And now we have the C-boundedness on a subset of the whole domain, which will be nearly the whole domain. We have again our expected value now restricted to the subset, and we have a fail probability. So this is the probability that we are outside of that subset C. This will be rather small. And then we have for epsilon bigger than this small constant, again, this concentration inequality. So we are, with our realizations, not far off the expected value. So that is the form of concentration inequality I want to use. So let's make it more specific. This omega n will be all possible data samples. And we have to think about how to choose Xi. This will be done in the following way. So this Xi will be all the samples where I have a uniform bound of that form. And this is quite common because a lot of the times you can say something about a subset of all samples where you have this uniform bound, or if you have a statement that with high probability the you have a uniform bound, then you are exactly in that setting. And with that, you can now show that the risk functional is C-bounded, as well as the cross-validation score. So we can apply the concentration inequality from before. And for now, let's fix H. So for a fixed model and fixed parameters, you have some expected value, which is like the bold line here. And all realizations lie within an interval around that with high probability. So let's say 90% of the times you are within that interval. Now you can do this for different models or different parameters, as in Tikhonov regularization, as Bernadette Hahn or Fabian Parser did on Monday. So you have here this curve for different parameters, and you now end up with a tunnel. And you cannot do this only for the risk functional, but you can do this for the cross-validation score itself. But I promised you to bring these two together. For now, we have just two separate concentration inequalities. And we will bring them two together by bringing their expected values, so these two bold lines together. And this is done by the following lemma, which states exactly that. So the expected value of the risk for n-1 samples is the same as the expected value for the cross-validation score. So these two images from the slide before can now be overlapped. And this is what you can see here below. So their expected values are nearly the same. And having that, we can now formulate our main result. So we have set our samples, so n samples as before. We have gamma, the fail probability that our uniform bound will not hold, which will be quite small. Then for epsilon bigger than some small constant, we have that the probability that the difference of cross-validation score and risk is bigger than epsilon will be quite small. So instead of computing the risk, which I cannot do, I can now compute the cross-validation score. And with high probability, I am only off by epsilon. So this here is a validation for the cross-validation score, basically. And to make it a bit more precise, so to give an example, because this is a rather abstract machinery, let's apply this to a concrete setting. So here we have Shepard's model. This is a special case of moving least squares. The model looks as follows. So it's basically a local convex combination of the data values. And you have here a kernel involved. For a kernel, we just used a simple head function, and we had a parameter in there which controls how narrow or how wide this kernel is. You can see below here three pictures for different width of the kernel. And you immediately see that the quality of the reconstruction heavily depends on how I choose this parameter. Okay, so now collect all the constants. I need to apply our general theorem from before. The first two I can bound rather easily. I just said that Shepard's model is a convex combination. So the first two can be bounded by the uniform norm of F itself. For the latter two, namely the uniform bound and its fail probability, I have to work a bit more, but it's also possible. So we've proved that if you have a local kernel and you assume F to be Lipschitz, then you can bound the uniform norm by the Lipschitz constant times the support of the kernel with this probability. And this probability, if you would fix n and the kernel is not too narrow, this probability is quite small. So we are fine with that. Okay. So we have everything together and we can apply our general machinery. So here we have the theorem just in a setting of Shepard's model. We have again these n samples. We have now our locally supported kernel. This is the fail probability from the slide before. Then for epsilon bigger than this small constant, we have that we can bound the difference of cross-validation score and risk with high probability. So instead of computing the risk, which I cannot do, I can compute the cross-validation score, and I'm not far off. Okay, and let me also show you a numerical example. So here for 50 different width of the kernel parameter, I did 1,000 experiments each. So we drew samples randomly 1,000 times for each parameter. And then we computed the cross-validation score as well as the risk functional. And let's choose a better visualization that we can see how our theorem works. So let's have a look at the lower left. Here we have these two bold lines are the mean values of all the experiments from up here. So the pink one being the mean value of these cross-validation score experiments, and the black one from the risk functional. And these transparent shapes are where 90% of the experiments landed. So these are the tunnels from before. And a dashed line are our theoretical bounds for that. So you can immediately see that there is a kink here. This is due to the kernel being too narrow, and we cannot do this gamma, this fail probability will get too big. But this seems quite natural, as you can see here, many outliers happen from here on. So this is as expected. The second thing you see is that we are off by a multiplicative constant. But if I would pull our theoretical bound down here, it seems like it fits quite good. So in terms of the order, it seems like we have found a pretty good bound there. And on the lower right, we have the same for the difference of cross-validation score and risk. And well, the conclusion here is basically the same as on the lower left. So with that, we have validation basically for cross-validation, also in the pre-asymptotic scenario. All right, thanks for your attention.